Hello everybody. This video is for MME 2305, Material and Energy Balance. I'm the instructor, David A. Robertson. I'm a professor here at UTEP. I can be reached at drobertson@utep.edu should you have any questions, or if you're in class, you can come ask me questions in class. The purpose of this video is to familiarize you guys with some topics and some techniques that will be very, very helpful when we get to the material balance portion of the class, which will come up quite shortly. The four main topics we're going to talk about today are flow rates, mass, mole, and volume fraction, molecular weight, and finally, concentration. Boom! Okay, we got camera firing on all cylinders, sort of. The rates we tend to care about in this class are mass flow rate, volumetric flow rate, and molar flow rate, okay? And you know it's a rate because of the dot. So a dot signifies a rate, okay? So in other classes, you may be given epsilon dot, and so that would be strain rate, and that would be in millimeters per minute. Okay, so strain rate is given in terms of millimeters per minute. So logically, you can assume that mass flow rate is basically given in units of mass over time. Volumetric flow rate is units of volume over time, and molar flow rate is units of moles, or number of moles per time, rather. So let's start off with mass flow rate. M, okay? So example units of mass flow rate would be grams per minute, kilograms per hour, kilograms per second, pounds mass per hour. We could do grams per day. Any unit of mass over unit of time would be essentially a mass flow rate. Let me adjust the camera a tad because it's not showing us what we want, and my chicken scratch isn't doing people many favors. Okay, so mass flow rate. So let's take an example of a time that we would be messing with mass flow rate. Okay, we would have maybe titanium dioxide would be a good example. And let's say we work in a paint factory, so we're flowing some titanium dioxide into some sort of mixer. We're making paint. Just as kind of an aside, titanium dioxide is the pigment that makes paint white. Before people used titanium dioxide, they were using lead, which is kind of hazardous to human health, so we no longer use that as a society. If you take an air sample in like a general neighborhood, you're more than likely to find titanium dioxide in your air sample. If you did that in the 1960s, you would actually find lead oxide, which is a little concerning. Okay, so we have titanium dioxide, and we have a mass flow rate, M. And let's just say we have a mass flow rate of 100 grams per hour. And we're asked to find the volumetric flow rate. Or let's just put what is the volumetric flow rate? Well, we see that mass flow rate is given in terms of mass per time. Let's take a quick look at volumetric flow rate. So volumetric flow rate is units of volume per units of time. So an example of that would be centimeters cubed per second, liters per hour, meters cubed per minute. We could do centimeters cubed per day. So any unit of volume over unit of time. So we want to get from mass flow rate, which is units of mass per unit of time, to volumetric flow rate, which is units of volume over unit of time. And it just so happens the material property of density can be used as a conversion factor because density is mass, density is mass over volume. So an example unit of density is grams per centimeter cubed. Okay, so we take a look at our little problem we've made up here. We're flowing 100 grams per hour of titanium dioxide into this paint mixer. And we want to know what the volumetric flow rate of titanium dioxide is. So we start off with 100 grams per hour. We're using our railroad track method in this class. And if you've not seen the video, I implore you to go take a look, especially if you're taking this class. So 100 grams per hour. And for bookkeeping purposes, I should have put titanium dioxide in there. So 100 grams per hour of what? Because as the problems get more and more complex in this class, bookkeeping is essentially the key to survival. And we'll go over that a little bit more in future lectures and videos that accompany this class. So it just so happens that the density of TiO2, according to my handy dandy research I painstakingly performed before making this lecture. This is really, really bad notation. So density, here, just excuse this. Density of is 4.23 grams per centimeter cubed. All right. So we want to make sure our grams cancel because we want to end up with units of volume per units of time. So if the density of titanium dioxide is 4.23 grams per centimeters cubed, we want to make sure our 4.23 is in the denominator part of this calculation. And we want to make sure that centimeters cubed ends up on top. All right, so our mass flow rate is 100 grams per hour. We want to end up with a volumetric flow rate. So the units we want are centimeters cubed per hour. So let's make sure this is going to work. So yes, grams cancel. So if I divide 100 by 4.23, let's see, what do I get? I get 23.64. I believe in class we agreed just to report the first decimal point, so I would round up, and we're below 5, so we can just go ahead and report 23.6. And we're going to do centimeters cubed per hour. And always when you do some sort of calculation to note where your answer is. And I probably should have put equals V, but here, we'll just put it up there just for good bookkeeping. Dot. So we have our volumetric flow rate now of 23.6 centimeters cubed per hour. Now, the next flow rate that we're interested in is molar flow rate. Okay, so N with a dot on top is number of moles per time. Okay, so let's take the example of aluminum. And in some countries, it's aluminium with a different spelling, but in the United States, it's aluminum. So if you look at my handy-dandy periodic table provided by EDAX, makers of fine X-ray detectors, and you can't really read it. My camera's not the most premium camera. So you can look it up on Google or if you have your own periodic table, but the atomic weight of aluminum is 26.982. Now, most of you, if not all of you, have taken chemistry at one time in your life, and you're probably told that this means 26.982 grams per mole. But in this class, we deal with other types of moles, okay? So it is implied that since our units are grams, this is in fact a g-mole or a gram mole, to be more precise. Okay, so our units of mass are in grams, so the accompanying unit with the mole is gram mole. So it's implied, particularly in most chemistry classes, that it's a gram mole. In this class, we also deal with kilogram moles, and we also deal with pound mass moles. So we also deal with some imperial units in this class. And so it just so happens that the atomic weight of aluminum is 26.982. There's 26.982 kilograms per kilogram mole. And this sometimes blows people's minds, but there's also 26.982 pounds mass in a pound mass mole. Pound mass mole of aluminum. And I should probably be putting aluminum so we can practice bookkeeping from the get-go in this class. It's a good skill to build. So I know what people are thinking. They're thinking, man, well, what about like unit conversions? How can we have the same number assigned to a gram mole, a kilogram mole, and a pound mass mole? Well, atomic weight, molecular weight comes in, the unit conversion comes in when we're actually doing calculations, okay? So let's make up a quick calculation just so you guys can have an example. So let's say we have 1,000 kilograms of aluminum, and we want to know how many pound mass moles this is. Okay, all right, how many pound mass moles is this? So we'd set up our handy dandy railroad track method that we should all be pros at least by the end of the class. So we want to start off with 1,000 kilograms aluminum. And it turns out we want our kilograms to cancel, and we know there's 26.982 kilograms of aluminum in 1 kilogram mole of aluminum. All right, so we know kilograms of aluminum are going to cancel out. If we performed a calculation now, we'd know how many kilogram moles of aluminum there are, but that's not what the question is asking. We're wanting to know how many pound mass moles are there. Well, the conversion factor between kilogram moles and pound mass moles is the same as converting a kilogram to a pound, okay? And so there are roughly 2.2 pound mass moles. We go ahead and put aluminum in 1 kilogram mole of aluminum. And so we want to make sure our units are going to cancel. So kilograms of aluminum cancels, kilogram moles of aluminum cancels. And so we're left with pound mass moles of aluminum, which is what the question was asking for. And so if I type the numbers into my calculator, painstakingly type it in, I get the value of 81.5 pound mass moles of aluminum. So very simple. And let me tilt the paper a little bit more. Let me cover again what I just wrote in case you guys didn't see it because my arms are all over the place and stuff like that. So we had 1,000 kilograms of aluminum. We wanted to know how many pound mass moles that equated to. So we set up our railroad track method. So we start off with 1,000 kilograms of aluminum. We know based on the periodic table that there are 26.982 kilograms of aluminum in 1 kilogram mole of aluminum. The conversion factor we use to go from kilograms to pound mass is the number 2.2. So we plug and chug and we get 81.5 pound mass moles of aluminum. So if you remember, we got onto the subject of different types of moles because we were talking about molar flow rate, okay, N dot. So if I go to another piece of paper, we can kind of recap a little bit. So molar flow rate. And that's the number of moles over time. So let's make an example using, again, our friend titanium dioxide. Titanium dioxide comes in two polymorphs, just a fun fact. Anatiz, I'm probably pronouncing it wrong, and rutile, which is probably the more common of the two. Someone may want to correct me on that. I don't know. So titanium dioxide happens to have a molecular weight of 79.866 grams per mole. And hopefully you can read that. So 79.866 grams per mole. Let's go back to our first problem where we said we had 100 grams per hour of titanium dioxide going into our paint mixer. So we'll kind of recap or redo this. So we had 1,000 grams per hour. Oh gosh, getting my capital letters mixed up. Excuse me. Going into a mixer. And we know since this is the mass flow rate, we want to know what is the molar flow rate. So what is the molar flow rate? Oh my goodness. Okay. Well, we know that mass flow rate is given in terms of mass per time. And we know that molecular weight is given in terms of mass per mole. So we can use molecular weight as a conversion factor to actually get from mass flow rate to molar flow rate, which is where we want to go. So let's set up our railroad track. Here, I'll pretend I didn't make a mistake. 100 grams per hour, goodness gracious me. And I keep forgetting to do the bookkeeping. 100 grams per hour of TiO2. The molecular weight of TiO2, so there's 79 grams of TiO2. And even though I'm kind of doing a bad job in this example, please start getting in the habit of doing good bookkeeping. So we have 100 grams of TiO2. We have 79.866 grams of TiO2 in one. We can do Gmol TiO2. And then we get the answer of 1.3. So there's 1.3 gram moles, and I probably should have put this up top. 1.3 gram moles of TiO2 flowing per hour, and that's equal to our molar flow rate. All right, so we've gone from mass flow rate to molar flow rate, and that's actually pretty simple. However, if we're given a volumetric flow rate, we probably can't do it with just one conversion factor. So let's take a look at this. I'm not a betting man, but I would think we would need probably two conversion factors to get from a volumetric flow rate to a molar flow rate. So let's make up a problem. So let's say we have 200 centimeters cubed per hour. And again, man, I'm sorry. Titanium dioxide, it's flowing. And we want to know what the molar flow rate would be if we have 200 centimeters cubed per hour flowing through. Okay, so we said on our mass flow rate problem that the density of TiO2 was 4.23 grams per centimeters cubed. And so if we're trying to get from a volumetric flow rate, so we're trying to get from a volumetric flow rate to a molar flow rate. So we're trying to get from volume per time to moles per time. There's some in-between step, or one in-between step we have to make. So first we have to go from volume to mass, and then from mass to moles. Because molecular weight, and maybe there's this type of data out there. I don't know if there is such thing as a volume per mole table or volume per mole chart. Perhaps there is. Maybe Google it and we can discuss it if you find it. But for now, I'm going with what I know in my head, and I know that molecular weight's readily available on a periodic table, And I know that density is a pretty easy value to find for stuff. So we're starting off with 200 centimeters cubed per hour. We know that the density of titanium dioxide is 4.23 grams per centimeters cubed. So the first thing we want to get rid of is centimeters cubed. So we can just put in 4.23 grams per centimeters cubed. We don't have to flip the unit this time, like we did in the other example, so kind of pay attention to that. If you don't remember what I'm talking about, feel free to hit rewind. And we know our molecular weight of titanium dioxide is 79.866 grams per mole. So 79.866 grams, man, I'm doing this bad again, grams of titanium dioxide per gram moles of titanium dioxide. And technically, you should have put 4.23 grams of titanium dioxide in 1 centimeter cubed of titanium dioxide. So again, I implore you, keep the bookkeeping, kind of do as I say, not as I do. I tend to get in a rush when I make these videos and do stuff on the board. Maybe I need to take a couple of deep breaths before I do this stuff. So here we go. So let's see. Let's do a quick inspection of what we're doing. So we have centimeters cubed of TiO2, cancels out. Grams of TiO2 cancels out. So we're left with gram moles of TiO2 and hours, and so we're left with moles per time. So that is the definition of molar flow rate. So let's plug and chug through our calculator. Feel free to calculate at the same time. I try to do the best I can punching numbers, but I have been known to make mistakes. So we have 200 times 4.23. If you want to pay attention to the intermediary step, see if you can actually see it. I got 846, and you can divide it now by the molecular weight of titanium dioxide. So 79.866. And I get 10.59, so we can round it up to 10.6. And again, feel free to follow along. 10.6 gram moles per hour. And we'll do TiO2, and that's the molar flow rate. Okay, so the next topic we said we were going to talk about, if you allow me to tab, is mass, mole, and volume fraction. I kind of jumped ahead to molecular weight in my brain, so we'll talk about that after mass, mole, and volume fraction. So let me get back to the paper slide. Let's start with a fresh one. All right, so mass fraction, and this stuff becomes kind of important because we want to know the amounts of various species in our chemical processes or metallurgical processes and stuff we're going to talk about in this class. So mass fraction bad handwriting. Fraction. It's denoted in terms of xi. And so generally we write a general equation, and it is the mass of I, of your species I, over the total mass. Over the total mass. And so we can take a look at our kind of recurring theme of titanium dioxide. So let me tilt the paper a tad so you can see it a little better. So mass fraction x sub I is the mass of a species I over the total mass. And so this kind of assumes that you have species I, J, K. Okay, so if I were writing, and the total mass is the mass of I plus the mass of J plus the mass of K. So I'm going to do it in a little different way then I've kind of done it before. Usually, you can say stuff like, well, let's start off with the simple one. So I have a bucket, and the bucket has 100 grams of stuff. Okay, so the stuff it has 50 grams of pebbles. It has 20 grams of glitter. And it has, let's see, we have to get to 50, so 30 grams of fairy dust. All right, so we have a bucket. It has 100 grams of stuff. Okay, so that stuff is 50 grams of pebbles, 20 grams of glitter, 30 grams of fairy dust. I'm making my troll Halloween party or something, costume, I don't know. So we want to know what the mass fraction of fairy dust is in my bucket, and it's a quite simple operation. So the X of fairy dust is 30 grams over 100 grams. You all can probably do this calculation in your head. My brain has long since reached the downhill stages. So 30 divided by 100, and I get 0.3. If you multiply that value by 100, it's 30%. So that was a little simple example. You could almost have guessed it just by looking at the numbers because I started with a nice round number of 100. But anyhow, this is how a simple example of how you would calculate mass fraction. So let's do a slightly more complex calculation for mass fraction. So let's say we'll go back to our titanium dioxide example. Let's say we have 100 grams of titanium dioxide. Okay, so we have 100 grams of titanium dioxide, and we want to know what the mass fraction of titanium is. All right, so we would do X sub Ti. So what is the mass fraction of titanium? Well, we have to do a little bit of chemistry stuff here. So if you look at the stoichiometric relationship between titanium and oxygen, in 1 mole of titanium dioxide, there are 1 mole of titanium and 2 mole of oxygen. Okay, so we want to know what the mass fraction of titanium is. So we already know what the mole fraction is. Okay, there's a 1-to-2 mole ratio there. So there's a total of 3 moles. So the mole fraction of titanium is 1 divided by 3. And maybe I will do another kind of example of that. Anyway, so we first want to know how many grams there are of titanium in this. So we start off with 100 grams. And I made a slight error, which I will strive to eliminate in editing, so to speak. Here's my poor man's editing right now. So we're going to rephrase our question. So we have 100 grams of titanium dioxide. We want to know what the mass fraction of titanium is in our 100 grams of titanium dioxide. Again, to do this, we're going to have to use a little bit of chemistry. So we're going to start off. Oh, goodness gracious, the Dow leaps. That's nice. I'm getting news notifications. I'm not supposed to. Hooray. All right. We're going to start off with our 100 grams of TiO2, and I apologize for my error. And we had said earlier in the day that there are 79.866 TiO2 in 1 mole. Okay. And we said earlier that there are 1 moles of titanium, or there is 1 mole in 1 mole of TiO2. All right. And so the final thing we want, because we're trying to figure out the mass fraction of titanium, so that means we need to figure out the mass of titanium in 100 grams of TiO2. So where are you, periodic table? Here you are. Periodic table, titanium, Ti. Perdóname. Made a little mistake there. Hit my camera. And again, my camera's not the best. But here we're looking at titanium Ti. It has a atomic weight of 47.88. So we know there are 47.88 grams of titanium in 1 mole of titanium. All right, so we made this nice railroad track, and hopefully now you're getting the importance of both the railroad track method and the use of bookkeeping. So now, because we've switched species, if you've been paying attention, so we have titanium dioxide here, and we also have titanium here. So that's why this bookkeeping becomes very, very important. So we will cancel out grams of titanium dioxide. We're going to cancel out moles of titanium dioxide. And now we're left with moles of titanium and grams of titanium. Our moles of titanium will cancel out. And now we're just going to be left with grams of titanium. Okay, hopefully this makes sense. So we have 100 grams of titanium. We're going to divide it by the molecular weight, 0.866. And I'm just showing you guys the intermediary step. Hopefully you can read my fine TI calculator. I'm at 1.25 when I do that. And then you want to multiply it by 47.88 grams of titanium. And that is, I got 59.95. I'm going to go ahead and round that up to 60 just for easiness. I'm sure the more precise engineers in the world are seeing this and going, oh, that's kind of scary. Okay, so the mass of titanium is roughly, I'll just go ahead and put roughly 60 grams. Okay, so we were asked for the mass fraction of titanium, and so we know now, we started off, we were given our total grams of titanium, so that was 100 grams. 100 grams of titanium. That would be on the bottom. So it's 60 grams divided by 100 grams of titanium. So X titanium, and I apologize, I'm setting this up backwards, but if you just take a pause and take a look at it, we're figuring out the mass fraction of titanium is 60 divided by 100. Very simply, that's 0.6 or 60%. So the mass fraction of titanium and titanium dioxide is roughly 60% by our calculations. The other fraction we care about, as I said before, is mole fraction. And I kind of verbally did this. Mole fraction actually is given in terms of Yi. And why? I don't know. Haha, pun. Get it? Okay, Yi is mole fraction. And it is Ni over N total. Okay, so very, very simple. So if we want to kind of go back to what I verbally said, we want to know the mass fraction, the mole fraction of titanium, or more precisely, NTI in our titanium dioxide. The amount of grams is kind of irrelevant at this point. So we know if we say we have 1 mole, that is 2 moles of oxygen and 2 moles of titanium. Okay, so the total moles in this stuff okay, so we're taking a look at titanium dioxide, okay, and we want to know the the mole fraction of titanium in titanium dioxide. So more precisely, the mole fraction of titanium, YTI. And so that equals the number of moles of titanium divided by number of moles total. So in 1 mole of titanium dioxide, you have 1 mole of titanium and 2 moles of oxygen. Okay, so that means the total number of moles is 3. So there's total number of moles is 3. So the mole fraction of titanium equals 1 divided by 3, essentially. And so, yes, I'm using a calculator, which is a third. I don't know why I felt I needed the need to do that, but it's roughly 0.33 or 33%. Volumetric fraction is another thing we talk about in this class, particularly when we're dealing with exhaust gases for like furnace problems and stuff like that, which we will definitely get to. So let's think about a furnace, and we'll think about kind of the products of combustion gas. And let me think a little bit. So stuff we generally have in combustion gas, we probably get some O2, and we probably have some carbon monoxide. We probably have some carbon dioxide, and we potentially have some nitrogen. And we'll talk a little bit more about nitrogen and air. In general, in this class, we say that air is 79% nitrogen. And hopefully you can read air. And it's also 21% oxygen, but diatomic oxygen. So be careful of the diatomic nature of O2 that we have in our gases here. And hopefully you can read air. But air is generally nitrogen and oxygen in this ratio of 79 and 21%. An example of gases that we have in typical exhaust is oxygen, carbon monoxide from the combustion process, carbon dioxide from the combustion process, and then nitrogen also from air, which is generally inert, so we don't really consider it in reactions, but we have to consider it in terms of a mass balance. So let's take a quick look at an exhaust gas. Let's say we can look at it from 2 ways. So let's say we have 10 liters of oxygen, let's say 20 liters of carbon monoxide, 45 liters of carbon dioxide, and I don't know, let's do 25 liters of nitrogen, okay? And you want to get you're posed with the question, what is the volume fraction? Volume fraction, I apologize for not writing it already, is this V sub X. In the notation we use here, and is V of a species I over, you guessed it, V total. Okay, so VI, so let's say we want to know what the volume fraction of carbon dioxide is in this. So what is, gosh, I can't spell. What? Sorry. What is VCO2? All right, so VCO2. So first we got to tabularize the total amount of liters in our exhaust gas. So we took a sampling, and this is what we got. So 10 plus 20 plus 45 plus 25. 10 plus 20 plus 45 plus 25. And that just kind of happened to equal 100. I actually strove not to. I think subconsciously I did, just to make the calculation easier. So 100 liters total. And we want to calculate our VCO2. So our VCO2, this is probably going to be way simple by this point in time, is 45 liters over 100 liters. And that equals 0.45 or 45%. Another way that we are given problems in terms of fraction, okay, is kind of doing these problems backwards. And I'll do one just for volume fraction. And the same thing kind of applies to mole fraction and mass fraction if you're given a similar problem. So kind of be aware of that. So let's take a look at our exhaust gas again. And so we have O2, and it is 16%. And we have, again, our friend carbon monoxide. I don't know if it's actually your friend. I wouldn't breathe it. We'll say it's 4.0%, so it's somewhat clean. We say we have some CO2, and that's 17%, and we put 17.0. And so we have, again, our nitrogen, and we say our nitrogen has 63%. And so let me make sure this kind of has to add up to 100. And that's 96.4. I made a mistake somewhere. Oh. Actually, this is 4. So yes, it adds up to 100. My bad. No, I cannot do this in my head. I'm just not that good. But anyway, let's say we have a 1 cubic meter exhaust gas. And it has this composition. Okay? And we want to know what is the volume of CO2 in this? Well, let's pick another one. I think we picked CO2 that time. What is the volume of O2? So what's the volume of O2? So we have 1 cubic meter. And you can take a ratio. So you can take what's called a basis. Okay, so we're actually given 1 cubic meter. Let's change it. We can say we have 3 cubic meters of exhaust gas. Forgive me for kind of changing gears on you. So 3 cubic meters of exhaust gas. What is the volume of O2 if our composition is this? So we start off with 3 cubic meters of exhaust gas. Okay, so we can employ. All right, I had kind of a technical difficulty. Back to this gas problem. So we have 3 cubic meters of exhaust gas. We want to know what the volume of O2 is. So we start off with 3 cubic meters of gas. If you look at the relative compositions, it's 16%, 4%, 17%, and 63% for O2, CO, CO2, and N2 respectively. So we can kind of take a look at what that amount is in 1 meter cubed, or 1 cubic meter of gas. And if you look at it just kind of by inspection, you can say it has 0.16 cubic meters of O2. So we can apply that factor to this. So 3 cubic meters of gas. In 1 cubic meter of gas, there's 0.16 cubic meters of O2. Our cubic meters of gas will cancel, and we'll end up with cubic meters of O2. So 3 times 1.6, 3 times 0.16 equals 0.48. All right, so we've solved for the amount of O2 in our exhaust gas. All right, the next topic we said we're going to talk about is molecular weight. And more correctly, we're going to talk about average molecular weight. So we've already seen a little bit about molecular weight when we looked at the molecular weight of titanium dioxide. Hopefully you know the difference between atomic weight and molecular weight. Atomic weight is just the mass per mole of an individual atom, whereas molecular weight is the mass per mole of something that's a grouping of atoms like titanium dioxide, water, which H2O, etc. So we're going to talk about average molecular weight now. And so let me get back to this guy. And so average molecular weight is denoted by the symbol M with a bar over it, and it should be a capital M. I didn't draw it too well, but M bar is average molecular weight and that is the summation of the mole fraction of what you have. Okay, and it should probably be I equals N or something like that. Forgive me if I'm doing my summation notation poorly. Times the molecular weight of an individual species. Okay, so the mole fraction times the molecular weight. And so the example I'm going to use is that of air. Okay, so we said earlier air is 79%. 79% oxygen, or sorry, nitrogen. Excuse me. My mouth wasn't doing what my hands were doing. 21% O2. So nitrogen and oxygen in this form are both diatomic, therefore they're both molecules. So we can use this as a decent example to show folks the concept of average molecular weight. So this ratio applies to volume. And you may remember this from chemistry, but the volumetric ratio of an ideal gas equates to the molar ratio of an ideal gas. So remember that because it comes in handy later in class. Volume ratio and also molar ratio. And again, this is a rule that applies to ideal gases. I'm sure it was named after a scientist whose name I've probably forgotten now. In this case, let's do things in terms of kilogram moles, just to get people familiar with the units. So the way we would write it, so we look at our summation notation, okay? So we have mole fraction times molecular weight, okay? And so we want to set up a summation now. So the molecular weight of air is equal to, so our molar ratio, we can also put slash if we want to keep semantics, or I guess consistent is the word I'm trying to look for. So the average molecular weight of air is the combination or the summation of the mole fraction of nitrogen in air times the molecular weight of nitrogen or diatomic nitrogen plus the mole fraction of oxygen in air times the molecular weight of the diatomic oxygen in the air. And so to write that out quite simply, and it doesn't really matter the units, but we'll just use kilogram moles for funsies. So 0.79, which is the YI of nitrogen, times molecular weight of nitrogen. So there are 28 kilograms, in 1 kilogram mole of N2 plus 0.21, and I probably should put air somewhere, and it's not going to cancel, so it gets kind of goofy, but 0.21 moles of O2, and we'll put kilogram moles. Okay, that's the fraction in 1. And I should have put this, so 1. All right. and I should have put 0.79 kilogram moles. So forgive the bookkeeping. This one's a little bit better. Sorry about that. Okay, and there are 32 kilograms of O2 in 1 kilogram mole of diatomic oxygen. Okay, so we've set it up, and I apologize for my poor bookkeeping methodology again, but let's kind of carry it down here. Is equal to 0.79 times 28, and that's, oops, excusez-moi, 22.1, and plus 0.21 times 32, and that's 6.72. And the units, I struggle doing this portion of the course always, and I'm sure there's somebody who knows how to do this a little better than I, maybe even a better YouTube video. But you add them together, and that is equal to 28.82. And so I think in this place it would be kilograms per kilomole, or kilogram mole. And so again, the same rule applies. There's the average molecular weight of air is 28.82 grams per gram mole, and 28.82 pounds mass, pound mass mole. All right. The next concept that we said we're going to talk about, and this will be probably the more simple of them, is concentration. And when we talk about concentration, we generally talk about molarity. And you've probably had this also in chemistry, and we'll kind of just cover it one more time. And let's see. Boom. Okay, we're back to our camera. So concentration. Okay, and so concentration, when we say we have a 1 molar solution of something, let's just say we have a 1 molar solution of salt water or something. Okay, so 1 molar solution, that means there are 1 mole of sodium, or sorry, salt, this is sodium chloride to be more specific, in 1 liter of solution. All right, so that's what molarity means. So 1 molar, if we have a 1 molar solution of sodium chloride, that means there's 1 mole of sodium chloride per 1 liter of solution. All right, so we'll do kind of a simple example of this. And let's say we have 10 liters of a 1 molar solution of NaCl. Okay, so we have 10 liters of a 1 molar solution of NaCl. So it's very simple. We want to know how many moles is there. question mark. Okay, so we'd start off with 10 liters, and 1 molar means there are 1 moles per liter. So that just simply means there's 10 moles. And I probably should have put 1 mole of NaCl here for bookkeeping purposes. All right, sorry about that. Okay, so here we were just using molarity as kind of a conversion factor. So let's look at a slightly more complex type of problem. And we'll stick with sodium chloride, and we'll stick with a 1 molar solution of sodium chloride. So we have 1 molar sodium chloride. Let's say this sodium chloride has a density. Actually, let's put it in terms of specific gravity, and I'll show you why in a little bit. So it has a specific gravity of 1.06, okay? And the reason why I'm saying specific gravity instead of just density is we're going to be doing things in terms of kilograms and cubic meters instead of grams per centimeter cubed. And so using specific gravity is just slightly more easier. So let's say we have this 1 molar solution, and it's flowing with a volumetric flow rate. Okay, so it has a volumetric flow rate of, let's see, what's a good number? Let's do 1.25 meters cubed per minute. Okay, and we know the specific gravity is 1.06, correct? And we want to know what the mass concentration of this is. Okay, so what is the mass concentration? All right, so we want to know what the mass concentration of sodium chloride is. And so we probably want to start with figuring this out, I guess. So I'm kind of pausing too much, I think. So we want to know the concentration of sodium chloride. And so we want to know that in terms of kilograms in a cubic meter. Okay. And so we want to first take a basis. In this case, we're taking a time basis. And there will be other instances where we are forced to take bases, and I will probably cover that in class or another video. But here we're taking a time basis because we want to eliminate the unit of time from this. So we're just going to say a time basis of 1 minute. So then we can kind of do everything without time because we're knowing that this is just happening in a snapshot of 1 minute. Okay. And so we know our concentration of sodium chloride. So let's kind of use some notation to start our calculation here. And we want to start off with what we know. So we know we have 1 mole of sodium chloride in 1 liter of solution. All right, so we have 1 mole in 1 liter of solution. And the molecular weight of sodium chloride is, I'm going to go ahead and put it in terms of grams per mole so we can kind of do a conversion. Hold up. All right. So there's a trick that I need to kind of point out before we carry this calculation on a little bit further. So you know there's different types of moles. We talked about it. So there's gram moles, kilogram moles, and pound mass moles. When we're talking about molarity, okay, and we say there's 1 mole in 1 liter of solution, when we say we have a 1 molar solution, this is actually gram moles, okay? So we don't want to forget that, because the next conversions we make basically are done because we have to take this in terms of gram moles. So there's 1 gram mole in 1 liter of solution. Okay, so the conversion factor here becomes really, really important. And so the molecular weight of sodium chloride is 58.44 grams of 1 gram mole. 1 gram mole of sodium chloride. And if you look here, our unit is meters cubed. And so out of convenience, we want to do everything in terms of meters cubed and kilogram. And so we're going to go through and do that conversion. So 1 kilogram is 10 to the power of 3 grams, or 1,000 grams. I kind of put it in 10 to the power of 3 just because I'm kind of running out of room in my paper. And a liter to cubic meter is there's 10 to the 3 liters, or 1,000 liters in a cubic meter. All right, so I'm gonna kind of plug and chug here. It shouldn't be too complex. And the thousands kind of cancel. So you have 58.44 in a cubic meter. So that's the mass concentration. There's probably a simpler way to do this, but kind of chose to do it this way. Let me see. The reason why I kind of chose to do this is because we're given a volume fraction that's in terms of cubic meters, okay? And so we want to have our answers in terms of cubic meters, because the next question, which would be an obvious question to ask, is what is the mass flow rate of this stuff, or what's the mass flow rate of sodium chloride in this solution if we have this 1 molar solution of sodium chloride going with a volumetric flow rate of 1.25 cubic meters per minute. So we want to know what the mass flow rate is. And so let's say we want to know the mass flow rate per second. Okay, just for funsies, okay? So we know our volumetric flow rate is 1.25 cubic meters per minute. And we know we have a mass concentration, which we calculated up here, of 58.44 kilograms per cubic meter. Okay, and just so it turns out, we want to be finding this in seconds. Okay, and we know we're going per minute, so we'll just do 1 minute over 60 seconds. Okay, and say, are we going to get our mass flow rate? Let's check. So meters cubed cancels. Minutes cancels because we want to know it in seconds. So we're going to end up with mass per second. So yes, we will get a mass flow rate if we plug and chug with our handy dandy calculator. So 1.25 times 58.44 and divided by 60. And so the mass flow rate of sodium chloride in seconds, is 1.2 kilograms per second. Okay. Now, to kind of tie everything together with other concepts we've talked about today, why don't we talk about the mass fraction of sodium chloride in our solution? Okay, so what's the mass fraction? Let me write. What is that? Man, I'm writing it horrible. In our solution. All right, so that's going to be the ratio. Okay, so the mass fraction now is going to be, we can do it in terms of mass flow rates. So it's going to be the mass fraction of sodium chloride. I'm sorry, the mass flow rate of sodium chloride times divided by the mass flow rate total of your solution. Okay, so we already calculated the mass flow rate of sodium chloride in seconds. So we already did that. And now, earlier we said it was a specific gravity of 1.06. And so if you remember from the activity we did in class, specific gravity is you get your density by multiplying your specific gravity times you get your density by multiplying the specific gravity times the density of a reference. And the reference is generally water. And in this case, water is 1,000 kilograms per meters cubed. So we want to get the density of our solution. And we want to have it in kilograms and in terms of kilograms and meters because that's the units we're dealing with for this problem. If we're dealing in grams and centimeters cubed, we'd be multiplying it by another number, namely 1 grams per centimeters cubed. But in this case, we're going to do 1.06 times 1,000 per meters cubed. Okay, so 1.06 times 1,000. So we have 1060. All right, so that is our density. Okay, so why do we bother doing this? Why do we bother finding our density? Well, we learned very earlier in this video that density can be used as a conversion factor between mass flow rate and volumetric flow rate. And we want to know the mass fraction of sodium chloride in our solution. And to get that, we need to know the mass flow rate of sodium chloride, which we've already calculated, divided by the mass flow rate of our solution, or mass flow rate total. And we were given a volumetric flow rate of our solution, yes? So we have to convert that volumetric flow rate to a mass flow rate. And to do that, we use our old friend density, which we just calculated from specific gravity. We use specific gravity in lieu of just saying grams per centimeters cubed because we're dealing with cubic meters. Okay, so we used our reference density of 1,000 kilograms per meters cubed for water to get where we're trying to get to. So the mass flow rate of our solution, in this case, excuse me, camera, in this case, mass flow rate of solution, we want to have it in terms of kilograms per second. And because we wanted to keep our units consistent, because in this case, just for funsies, I said, hey, man, what's the mass flow rate of sodium chloride in seconds instead of minutes, just to make it that much harder. Hooray. Okay, so we have a mass flow rate of 1.25, sorry, volumetric flow rate up here, volumetric flow rate of 1.25 meters cubed per minute of solution. Okay, always good to have some sort of bookkeeping that can keep yourself straight. We know we have 1060 All right, so 1060 kilograms per cubic meter of solution. Okay, so, we also know that 1 minute is 60 seconds. So let's see. Are we going to get the mass flow rate of our solution in kilograms per second? Let's check it out, folks. So cubic meter cancels, minutes cancels, so we're going to end up with kilograms per second. Yes, we're safe to fire up the old TI calculator. I don't receive money from TI, but I have a TI, which is not working right now. Clear. Yes, here we go. So 1.25 times 1060. I didn't show this on some of these, but I've been kind of showing the intermediary steps, so I got 1325. You can see my beautiful reflection, I think. And divided by 60 seconds. And I got 22.1 if we round up kilograms per second. And I'll double check. Yes, I got 22.1 kilograms per second. So up here, we said the mass fraction of our solution would be the mass fraction or the ratio. I'm sorry, what is the mass fraction of sodium chloride in our solution? Okay. And so it's going to be okay because seconds are going to cancel. So we're going to end up with all the units will cancel actually. And so we're going to end up with a nice ratio. So we said, and I should have done it this way, I apologize. So the mass fraction of sodium chloride, if you can read that chicken scratch, is the mass flow rate of sodium chloride divided by the mass flow rate total. So the mass fraction of NaCl, good old-fashioned table salt, is the ratio of 1.2 kilograms per second. I'm not really doing the railroad track method because you kind of know the units are going to cancel. Feel free to do the railroad track method if you see fit. 22.1 kilograms per second, and that equals 2. Come on, TI, bear with me. Divided by 22.1. 1.2 divided by 22.1 equals 0.05. Or if we multiply that times 100, we'll just go ahead and put 5.4%. I had some extra digits on my calculator if you care to inspect. Anyway, that concludes the video. If you have any questions, feel free to ask me in class or send me a quick email. I do warn you, I get bombarded with emails. I do apologize for any goofiness in the editing. I am doing this on a shoestring budget, so hopefully it's beneficial to you. And thank you very much, and have a good time doing mass and energy balances.